Okay, so we're going to get into, well, eventually we're going to get into AC power generation. But we got to put a couple of other things in place before we do that. The first thing is Amps law. Now, basically, what this says is if I have a wire, actually, if I have a moving charge, let's do it that way. If I have a moving charge, okay, well, as that charge moves, it will throw out into space around it a magnetic field. Okay, a magnetic field. So when charges move, they throw out a magnetic field sort of at right angles to the direction that they're traveling. So how does this manifest itself? Well, basically like this. Let's say that we have a wire which is filled with moving charges. Now this is going to bother some people, but the moving charges are considered to be positive, okay? That's traditional electricity or classical electricity motion. Okay, so we say then, another way of saying this is that current in this case will flow in this direction, positive to negative. So how we map the field here, okay, the field will exist in a circular pattern around here, and the way to work out what the field does is to use what's called the right hand rule. So you're going to take your right hand and you're going to point your thumb in the direction that current is flowing. So that's I. And so you're looking at your right hand, and then your fingers are going to curl around like this. Okay, and they're going to show you that the magnetic field is going to point around in that direction. So in this case, like this. Now this is not a great way to represent this in 2 dimensions. It's slightly confusing. If we were to take a slice out of here, so traditional nomenclature, right, if we split this in half, is to say then that the magnetic field on the bottom will be shooting away from us and on the top coming towards us, okay? The way to remember that way of drawing it is to imagine that you are watching an arrow. You're an archer, you're watching the arrow. If you see the arrow flying away from you, you're going to see the X of its feathers as it flies away. That's a terrible arrow. You just fix that. Okay, you'll see the back end of it as it flies away, and it's going to look like an X. And if the arrow is flying towards you, you're going to see the tip, and it's going to look like a dot. Okay, so you can see how this curved magnetic field looks like that. And by the way, how we represent magnetic fields to begin with is always in this manner: out of north and around and back into south, like that. So you can think of this then arrow as the direction that a compass would point if we were to put it in here, right? So you take a compass, and the compass is always going to point in the northerly direction wherever I put it, okay, all around here. So there we go. There's Amps law. So we know that a moving charge creates a magnetic field, okay? We can also create an electromagnet. Words are hard all of a sudden, and I'll show you how to do that. So let's start with this. This is just going to represent, this is going to make it easier to draw, okay? Let's just imagine that you have a coil of wire now, okay? So a coil of wire, just a loop of wire. All right? And now what I'm going to do is I'm going to say there's nothing actually in here. That's gone, okay? So to represent that, we'll draw like a ghost, a ghost piece in here. Because what we want to do is we want to say, well, if I run current into here, right? If I make this positive and I make this negative, then what's going to happen is related to Amps law, right? I'm going to get, what's going on here? I'm going to get current flowing in this direction. Like so. Okay, it's going to come over the top. It's going to come down in the front. It's going to go up in the back, over the top, and down here. Okay, so it's going to be flowing around like this. Now that's totally confusing, so we're going to simplify it. We're just going to say in front, current is going down, right? In front here, in the front loops, current is going down, okay? Here it's going up, but that's in behind. So this will produce a magnetic field inside of it that is the sum of all of these wires working together. So if I think about it, it's like I take a bunch of these wires, I loop them up, and I put them in a row side by side. Well, that magnetic field can't wrap right around, so it just adds on to the next one, to the next one, to the next one, to the next one, and so on, till we get to the end of the loop of wire. So remember, there's a coil of magnetic field attempting to go around here, but because of the way this is set up, and you'll have to use your imagination here, there's this little vortex of electric field or magnetic field spinning around here, and those are going to sum. Okay? And what will happen, if you think about it, is you will end up getting a magnetic field that behaves as if there is an invisible bar magnet sitting inside this loop. And you can measure this whole thing with your compass. So there's a cheater rule to figure this out. You can use Ampe's law, okay? You can use Ampe's law, and you can say, okay, if I point my thumb down, then my fingers are going to wrap inside the loop, and then north will be there and south will be here, out of north and into south. But the cheater rule is actually even easier. You are going to take your hand, and you're going to imagine your right hand, and you're going to imagine that you grab the solenoid with your fingers pointing in the direction of the current. And then your thumb will point to north. So try that, imagine that. So imagine you have to be behind here, right? Here you are, I'll draw you, looking at this thing. Okay, and then you take your right hand, and you just like grab onto this thing. And then your thumb is going to point off to the right, which will then be north. We call this the cheater rule, the cheater right hand rule for solenoids. You learned that last year. That's what it is. Look at this. This is a great drawing. There you are. There's your right hand grabbing, pointing in the direction of I, the current flow, and there is north. Cool. So now we know a few things. Let's talk about one more thing. If I have a solenoid, again, I have to do this little method of drawing a solenoid. I'm going to explain the way to think about this in just a moment. But let's say we loop up, make another solenoid like we just did. Put a few more loops on it, like so. Okay, so here I've just popped in an image of a solenoid. This is not bare wire, by the way. It might look bare, but it's not. It's got a clear lacquer coating on it. If it were not coated, then current would just, like if I hooked up, so basically I would hook up power, do that. I would hook up power to each of these, right? Like right into here, and right into here. Like that, or the other way around. And then I'd look and see, right? And I'd say, okay, the wire goes around this way. So current is flowing like this around here. Okay. If I hook it up this way and current's flowing that way, which way ends up being north on here? Yeah, this way. Because I grab it with my right hand and my thumb will point to north. Okay. So that's what a real life solenoid looks like. All right, tons and tons of wire wraps, and it will get a significant magnetic field built up around it. Okay, you can test that very easily. You can make your own, right? Take a nail or something, make a bunch of wraps with some shielded wire, pull the nail out, and there you go. Okay, so I'm just going to put my ghost image inside there. Actually, yeah, I will put my ghost image inside here. Now, it turns out that if I take a permanent magnet, okay, let's put the north side here. And let's actually not have any juice on here. Let's just leave it. But let's put an ammeter in here, or a galvanometer, or something, some way of detecting the flow of current inside this coil. So what this looks like in practice, it's an ammeter. But what it looks like is it'll have like a little arrow on it, and it'll have a plus side and a minus side. So what that's just detecting really is the voltage. Now, it turns out, if I bring this permanent magnet inside the solenoid. As this field is entering the solenoid's coils, it will push current one way, and as I pull it out, it'll suck current the other way. And if I keep this moving back and forth, okay, a potential will exist in here, and that potential will alternate from one side to the other. If I push, it goes one way. If I pull, it goes the other. So we've got some key things to think about. The first is this: conservation of energy. If I am creating a potential, right? If I'm building a voltage in here, well, I know a voltage is electric potential energy, and I know that work energy theorem, or conservation of energy, means that I must be doing work in order to generate this voltage. You don't get a voltage for free. So what that means then is that if I'm pushing this in, I must be working as I do so, because I know in another place in this circuit, a potential is being built. So I must be applying a force in this direction, okay? So what's going on? Well, what happens is this. The electrons, which are inside, or the charge carriers, I should be careful, the charge carriers, which are inside this wire, will react to a change in magnetic field. So change equals flux, right? You know this word for change is flux. Things are in flux, they're changing. Well, this is called magnetic flux. A change in the magnetic field is causing these electrons, or these charge carriers, sorry, inside here to react. They will react by moving, okay, which we will detect over here. They'll react by moving, which we'll detect over here. Or another way of thinking of it is, this flux, this changing magnetic field, is creating a voltage inside the solenoid. It's forcing the charge carriers one way or the other. But remember, I need to work to obey the law of conservation of energy. So as these move, right, remember Ampe's law, moving charge creates a magnetic field. So what ends up happening is these moving charges create inside the solenoid a field that will repulse what I'm trying to do. If I'm trying to push these in, these charge carriers will move in such a way that I end up with a north-facing magnetic field inside of here that will resist the insertion of this magnet, right? So if I'm pushing it in, it's making me work. That work is getting converted into potential, and I could actually put like a little light on here, and if it's a small enough and weak enough light, and I move fast enough and aggressively enough, I could actually generate, well, an alternating current. I could whip it in, the current would flow one way. Now, let's imagine that I flip-flop, and now I'm pulling it out again. So if I pull it out, I also have to be doing work, okay? These charge carriers will react to the diminishing flux, or the flux to diminish the field, by moving in the opposite direction. And what they'll do is they'll create a south-facing magnetic field that attempts to prevent this from moving out. So I will have to provide a force in order to pull it out again. So I work on the in. That makes the charge move one way and creates a north to resist the input. And when I pull it out again, I have to work in the opposite direction, which will cause charge to move in the other way. Okay? And you can imagine what would happen if I just flipped this over and I tried to jam the south in here. The same thing, it would just generate in the opposite, would generate a magnetic field in the opposite way. Okay? So we could say then, there's a law about this, and it's called Lenz's law. Lenz's law, which states that a solenoid will resist changes in magnetic field. Okay, there's a little more to it than that, but I think it's just easiest to think about it in this way. If I try to push a north in, this will create a north to resist that. And the way I like to think about it is it's conservation of energy. I need to work to generate potential. Either way that I go, potential is being generated, I must be working. If I'm pushing north in, north must be here because north magnets repel. North sides of magnets repel. If I'm pulling out, we must resist, so it must be attracted, and this must flip to being a south. Then I remember with Ampe's law, in order for there to be a field generated, that must mean that charges are moving. So I can figure out which way the charges will move based on this. So as I pull out, I get a south magnetic field. Which way is the current flowing? Use your cheater rule to figure it out. So the way to think about it is use your cheater rule, right? If I'm pulling out right now, if I'm doing work off in this direction, okay, if I'm pulling this way, this creates a south here because we need an attractive, magnetic force. Call that FB, B for magnetic field. And in that case, this side must be north. So I'm going to pretend I'm grabbing this with my thumb pointing to the north. Here's my thumb north. And then my fingers are going to wrap around the solenoid to show me current is going upward. If I change directions and I push in, this suddenly flips to north. My hand goes around, and then the direction of current flow must have flipped. So if I continually do this, insert and extract, I can cause current to constantly be flip-flopping inside this circuit. All right, no electricity or no generator that I know of works in this way. This is more just for classroom demonstration to show that it's true. Okay, let's see how we can use this concept, though, to actually generate electricity. So we're going to start out with a magnetic field. We're going to say that that magnetic field aims into the page. Okay, and magnetic fields are signified as B, and they're measured in what are called Teslas. I'm not going to actually, this isn't the right place to get into the unit of Tesla. It's not an SI unit. You can maybe just go do a little checking. There might be another video I have where I describe what Tesla is. If not, it'll come. If not, in the time you need it, go look it up. So I just want to do a little aside here. I want to imagine that I now send a charged particle, a plus, into this field. Okay? We're going to learn a new right-hand rule. Really, there's only three, right? There's the one with the coil that shows the direction of magnetic field around a flowing current. There is the cheater rule, which isn't the true rule, it's the cheater rule. And then there's this one, which is a true rule. So what we're going to do is we're going to put our palm flat of our right hand, okay? We're going to point our fingers into the page, the direction of our magnetic field. And we're going to take our thumb now. Our thumb is going to point in the direction of the velocity of our charged particle. Whoops. Some polydactyly there. Okay, so I wonder if I can draw this better. You know what I can do? All right, so if you have your right hand, the picture should say everything you need to know. If you're very confused about what you're seeing, I don't know how to help you. My fingers point in the direction into the page, right? The direction that this magnetic field is pointing, which is into the page. My thumb points in the direction of the velocity of the positive object. And then the last part of this is that there will be a force acting on this charged particle as it moves in the magnetic field. And that will point in the upward direction. So what it will do is it will tend to curl this charge as it enters the magnetic field in this direction. Because a force will exist always, and you can try this with your right hand, towards the center. So get this thing sort of spiraling inside of you. This force is often designated FB, force from a magnetic field, okay? So what happens then if this thing is actually now a negative? Well, I would do the exact same thing, except realizing that by switching it to negative, the force flips direction, and the negative will spin this way inside the magnetic field, okay? Okay, so what we can do with this is we can give you now a formula that describes what's happening here, and that is this. The force experienced, FB, is equal to Q, that's the size of the charge, the velocity, times B, the magnetic field strength. Okay, now there's a little bit more appended on here. I'll talk about that in just 1 second. Here's an interesting fact. Let's say we're looking at a magnetic field from the side. So this is now B. We're looking at this from the side, right? We've come over here and we're looking at it like this. So here's the magnetic field. You might have this inside, like, say, a horseshoe magnet, right? Where this is north and this is south. So sort of like a parallel plate system, but for magnets. Now, if I take a moving charge, and say I also put like an electric field here, right? Like I put a positive plate and a negative plate here. Like that. This charge will then be propelled by this electric field in this direction. However, there will be no FB. Okay? But if I take this charge and now I make it fly across the field, like from towards me to into the page, there will be an FB. Okay? Which direction will FB go in this orientation if I'm firing it in this way? Use your right hand rule to figure out which way the force would be. So we're going to take our hand, we're going to point our fingers from north across to south. Your palm should be facing the page. And then we're going to torque our hand over so our thumb is pointing in and your palm should aim towards the ground. FB on this positive charge now all of a sudden is down. So what's the difference? Well, it turns out that the magnetic fields of the moving charge and the permanent magnetic field will only interact with each other at right angles. Okay, so you get full magnetic charge or full magnetic force when it's going across the field and none when it's going with the field. So if it's moving in the same vector direction as the field, no FB is formed. What do you think happens at, say, like 45 degrees? Okay, I think maybe I didn't explain this quite right. Okay, so we are imagining that this is all in one flat plane, okay? It's really hard for me to draw something in 2D that's moving away from me. How do I draw that moving away from me? I have to like draw it like this. Like, I don't know, I could do like railroad track style. Like, there's the horizon. I don't know how to do that with a charged particle. I'm not a good enough artist. This is meant to represent something moving away from me through this magnetic field at the exact same height in the same plane as the one that was moving from left to right. The whole point of that is to indicate to you that if you're moving with the field in this direction, there will be no FB generated. However, if you move at 90 degrees to the field, you will get a full force. And then the question was, well, what happens at some angle? So this is like, imagine like a flat circle. If I look at the side of a circle, it just looks like a line, right? This should all be in a line, but one's going this way, one's going at 45, and one's going across the field, okay? So we're going to say angle-wise, this is at 0 degrees to the field. This is at 90 degrees to the field, directly across from it. I get full force when I'm going at 90, so I'm going to append onto here this little thing, sine of theta, okay? Now what that's going to do is it's going to moderate or modify how much of the FB is actually being created by how close to 90 degrees or what fraction of 90 degrees is actually interacting with the field. If it's 0, well, the sine of 0 equals 0. The sine of 90 equals 1. So it's like putting a 1 at the end, so you get just QVB if it's acting at 90. But if it's going at 45, you now get QVB sine 45, which is QVB times 0.5. So you get half of at that one, okay? So this is the formula then that tells you what the size of FB is. Let's try it. A charged particle is, I don't know, let's say like 10 microcoulombs. It enters a 4 millitesla electric field at, I don't know, 2 times 10 to the 8 meters per second. Calculate FB. So how am I going to do that? Well, it's pretty straightforward. FB is QVB sine theta. Oh, and one more thing. Let's say it enters at like 80 degrees to the field. At 80 degrees. Okay? So it's just fill in the blanks, right? So Q we said was, what did we say? 10 microcoulombs. So 10 times 10 to the negative 6 coulombs. 2 times 10 to the 8 meters per second. And then sine 80 degrees. Oh, and I forgot the field strength, which is 4 milliteslas. So 4 times 10 to the negative 3 teslas. Oh, it barely fits. Can we do this in our heads? Sorry, bad sig figs. Oh, yeah. Okay. Should be 7.9 newtons roughly. Let's talk about one more use of this. One more use, and then we're done review and we're on to new. Draw one more field. I just have a tendency, for whatever reason, to always want to draw them into the page. I think it's because for ease of like figuring it out, it's easier to point your fingers away from you than towards you. But what would happen if, instead of having a particle shot in there, like you might have at like say the Large Hadron Collider, which is looking to detect the charges and properties and so on of particles from, massive nuclear collisions, all right, or particle collisions. They use detectors with strong magnetic fields, and then they map the paths of particles through them. You can tell stuff about the particles. Well, what if instead of that, we have a wire? Okay, so let's imagine this is a wire. Actually, I don't want it to look like that. I want it to look different. I want it to look like an actual wire. So wires are like copper color. And here's a wire. Okay, now you're gonna have to wrap your head here. This wire is a perfect cylinder. Okay, it's a perfect cylinder. Actually, let's even just make it into a cylinder. Watch this. Watch this magic. Yeah, hang on. Just wait, I'm not done yet. I'm gonna put that there. Stretch it out a little bit. Just wait, not done yet. You'll see where I'm going here though. Stick along. Come along, children. Come along for the ride. Okay, here's a big fat copper wire. I'm going to sit it on top of, so we're looking down at this from above. I'm going to sit it on some tracks, which are also wires, and we're going to connect this all up to a voltage. Oh. Doesn't quite line up, but whatevs. Okay, so then this is positive and this is negative. So what will happen here, right, is we'll have current flowing through, and the current will move through this way and down in this direction. So if I'm thinking that current is positive charge carriers, and that's exactly what we have to imagine, what will the overall force on this wire be? Take your right hand, point your fingers at the screen, point your thumb in the direction of the travel of the charge. Your palm should be pointing upwards. If your palm is not pointing upwards, you're not doing it right. Fingers aiming into the page with the magnetic field, thumb pointing direction of current flow, palm points up. The sum on all of these charges adds together, and what you get is you get an overall force FB on this wire, and it will actually like begin to move. It'll start to move, right? It'll roll. We can actually cause physical objects to move in space using electromagnetism. And guess what? There is, of course, math. We know why the sine theta is on there, but now we've got magnetic field strength in Tesla. We've now got current in amps, and we've got whatever length of wire we have here in meters. So we have another way to figure out the force on a current-carrying wire in any magnetic field.